Hello everyone and welcome to this course on VLSI design. So in this course we will dive into the world of very large scale integration, which is also known as VLSI, a key technology that powers modern electronics. Whether you are a beginner or looking to refresh your knowledge, this course will provide you with a comprehensive understanding of VLSI design and its practical application in real world devices. So first, we will introduce the fundamentals of concepts of VLSI technology. We will discuss what VLSI is and how chips are made, including the basics of fabrication. We will also learn about transistor, the building blocks of VLSI circuits, and the foundational NOT gate that drives logic operation. In Module 2, Building Circuits, we will explore the process of designing circuits within a VLSI framework. We will cover logic circuits for mathematical operation as well as sequential circuits that handle memory. Additionally, you will learn about clocking, which is crucial for coordinating the operations within the chip. In the third module, we will teach you how to describe VLSI designing using hardware description languages like Verilog. You will also learn how designs are tested virtually through simulations and how quick prototyping with FPGAs helps in validating designs before fabrication. In Module 4, the final module will take you through the process of turning VLSI designs into physical chips. We'll cover the physical design arrangement, the importance of chip testing for the quality assurance, and the tools used by engineers to facilitate these tasks. So by the end of this course, you guys will have a solid foundation in VLSI design and be well prepared to explore more advanced topics in integrated circuit design. So basics of VLSI. So very large scale integration, VLSI is the process of creating integrated circuits, ICs, by combining thousands, millions or even billions of transistors into a single chip. VLSI technology has changed the world of electronics by enabling the development of complex and powerful devices like computers, smartphones, and more, all while reducing the size and power consumption of these systems. Before the advent of VLSI, the integration of electronic components on a chip was limited to just few transistors. However, as technology advanced, it became possible to integrate a massive number of components into a single chip, making circuit faster, more efficient, and more affordable. So in this module, we will explore the basics of VLSI, how chips are made, the roles of transistor as electronic switches, and how the NOT gate serves as the first building blocks in digital logic. So what VLSI is? VLSI stands for Very Large Scale Integration, which refers to the process of integrating a large number of electronic components, primarily transistors, onto a single chip. So these components can include not just transistors, but also diodes, resistors, capacitors, and other essential components needed for an integrated circuit, which is also known as ICs. So the number of components integrated onto the chip has been steadily increasing over the decades, from a few hundred components in early chips to billions of transistors on modern processors. VLSI enables the creation of complex circuits, including microprocessors, memory chips, and other digital circuits. It also allows for the miniaturizations for electronic devices, leading to the compact designs of modern-day electronic gadgets. In fact, modern processors include those used in smartphones and computers, contain billions of transistors in a space smaller than the fingernail. So the development of VLSI technology has had a profound impact on many industries including computing, telecommunications, automotive, medical devices, and consumer electronics. So the driving force behind VLSI is Moore's law, which says that the number of transistors on a chip would double approximately every 2 years, leading to exponential growth in processing power and reduction in the cost. So now let's see how chips are made, the basic fabrication process. So the fabrication of VLSI chip is highly complex and delicate process that requires advanced technology, precision equipments, and clean room conditions. So it involves multiple steps, each contributing the creation of an integrating circuit that can perform its desired function. So the basic fabrication process consists some following steps, which are: the first one is the design and the planning. So before any physical work is done, the design of the integrated circuit is created. Engineers use specialized software tools to design the chip's architecture, ensuring that the arrangement of transistors and the other components will perform the required tasks. This is crucial stage in chip fabrication, as the design directly impacts the chip's performance, power consumption, and overall functionality. The second one is wafer preparation. So the fabrication process begins with a thin slice of silicon known as wafer, which serves as the base material for the chip. Silicon is chosen because of its excellent semiconductor properties, which allows it to control electrical currents efficiently. So the wafer is carefully cleaned to remove any contaminants that could affect the chip's performance. The third one is photolithography. So once the wafer is prepared, the next step is photolithography, which is used to transfer the chip's design onto the silicon wafer. A layer of light sensitive material called photoresist is applied to the wafer. So the wafer is then exposed to ultraviolet UV light through a mask that has the circuit design. So the areas exposed to light undergo on a chemical chain, allowing the pattern to be developed on the wafer. The fourth one is etching. So after the photolithography step, the wafer undergoes an etching process to remove unwanted proportions or portions of the photoresist and underlying materials. So etching can be done using various techniques, including dry etching using plasma and wet etching using chemicals. The remaining material forms the transistor gates and other components of the ICs. The fifth one is doping. So in this step, the wafer is exposed to different chemicals dopants to alter the electrical properties of the silicon in specific areas. Introducing dopants such as boron or phosphorus makes the semiconductor material either conductive N-type or less conductive P-type. So this creates the region in the silicon where transistors will be formed. Then comes deposition. So the wafer may also undergo deposition, a process in which thin layers of materials such as metals or insulators are deposited onto the wafer. So these layers are used to form various components, including the interconnections between transistors, metal contacts, and insulation between the different layers. Then comes metallization and packaging. After the various layers are created, the wafer is subjected to a metallization process in which metal, usually aluminum or copper, is deposited to create electrical connections between transistors. So finally, the wafer is diced into individual chips which are packaged to be used in electronic devices. So now let's jump into the transistor, the electronic switch. So one of the most fundamental components in VLSI technology is the transistor. So a transistor is the semiconductor device used to amplify or switch electronic signals and electrical power. So it is essentially an electronic switch that controls the flow of electricity between two terminals. Transistors are at the heart of every digital circuits and are used to build the logic gates that forms the basis of all computational process. So their transistors are made materials like silicon, which have properties that make them ideal for controlling electrical currents. A transistor typically has three layers: emitter, base, and the collector. So the base controls the current flowing between the emitter and the collector, making the transistor either conductive or non-conductive, depending on the signal received. In VLSI technology, field effect transistors, FETs, are the most commonly used type. FETs are used because they are more efficient and easier to miniaturize than the other types of transistor. So the metal oxide semiconductor field effect transistor MOSFET is the dominant type used in VLSI circuits. Transistors can be used in digital logic circuits to perform operations like switching, amplifications, and signal processing. So these operations form the foundation of modern electronic devices, as transistors control the flow of binary data, zeros and ones, in the form of voltage levels. So now let's move forward and see the first building block, the NOT gate. We will learn about gates in next module as well, but let's start with the NOT gate. So the NOT gate, also known as inverter, is one of the simplest yet most important components in digital logic design. A NOT gate takes a single binary input and produces the output opposite. or you can see produces the opposite output. So if the input is 1, which is true, the output is 0, which is false. And if the input is 0, which is false, then the output is 1, which is true. So the NOT gate is the most basic building block in Boolean algebra and digital circuits, and it is used in many more complex gates and circuits. In VLSI circuits, the NOT gate is implemented using transistors, and it plays a crucial role in performing logic operations that enables the functionality of microprocessors and memory units. Boolean representation of the NOT gate, which is this. Okay, if the input is 0, then the output will come 1, then the if input is 1, then the output is 0. 0 means false and 1 means true. NOT gate in VLSI circuits. In VLSI circuits, a NOT gate is created using MOSFETs. The input voltage of the MOSFETs determines whether the transistors conducts or not. If the input is high, which is 1, one transistor is switched on, pulling the output low, 0. Conversely, if the input is low, 0, then the other transistor is switched on, pulling the output high, which is 1. So NOT gates are used in combination with the other basic logic gates such as AND, OR, and XOR gates, which we will learn in the next module, which will create more complex operations like additions, multiplications, and decision making in digital system. So in conclusion of module 1, the VLSI technology is the backbone of modern electronics, enabling the development of powerful, impact, and energy efficient devices. So in this module, we have explored the basics of VLSI, how chips are made, and the role of transistors as electronic switches, and how the NOT gate serves as the foundational building block in digital circuit. So the fabrication of VLSI chips involves intricate process like photolithography, doping, etching, and deposition. So transistors, specifically MOSFETs, are the heart of VLSI circuits, enabling the switching and amplifications of signal. So the NOT gate, one of the simplest logic gate, is built using transistor and serves as a first step in the construction of more complex digital circuits. So as technology continues to advance, VLSI will play an even more significant role in the development of future electronic devices, driving progress in fields such as artificial intelligence, quantum computing, and beyond. So understanding the fundamentals of VLSI will provide you with the foundation needed to dive deeper into the world of semiconductor design and digital electronics. So in the next module, we will learn about circuits. So in the world of VLSI design, building circuits is a critical skill. Circuits form the backbone of digital electronics, ranging from the simple logic gates to complex microprocessors. So these circuits are created using a variety of components that perform a specific task. They can be broadly classified into two types: combinational circuits and sequential circuits. Both play a crucial role in a digital system, but they function differently. Combinational circuits, such as those used in mathematical operations and the logical design, in contrast of sequential circuits, involve memory elements that store information about the state of the system and use in the historical data to make decisions. So the circuits built using two types of logics are the building blocks of all digital systems. In addition to combinational and sequential logic, the concept of clocking is essential to the operation of many digital circuits, as it helps synchronize various processors within a chip. So in this module, we will explore the basics of building circuits, starting with the logic used for mathematics and decision making, which is combinational circuits, followed by the logic for memory and state dependent operations, which are sequential circuits, and finishing with the clocking, the rhythm that keeps everything in the sync. So what are combinational circuits? Combinational circuits are circuits whose output is a direct function of their current inputs. In other words, the output is determined solely by the current input values and it does not depend on any previous inputs or states. So these circuits do not have memory and cannot retain any information about the past events. Combinational circuits are fundamentals for performing logical operations and mathematical calculations. So they are the building blocks for more complex operations and are the foundation for the arithmetic logic units ALUs in the processors, which performs calculation and decision making tasks. Let's jump to the basic logic gates. So combinational circuits are typically built using basic logic gates or logic gates, which are the fundamental building blocks of digital electronics. So these gates perform basic operations on binary input, zeros and ones, and produce a single binary output. So each gate has a specified logical function based on the Boolean algebra. So the most common logic gates include, the first one is AND gate. An AND gate outputs 1 true only when all its inputs are 1. It mimics the logical AND operations, meaning all conditions must be true for the results to be true. If any output is 0, the output is 0. Here you can see the graph, the truth table. If the input is 0, then output will be 0, because it's AND, A and B input. If input A is 0, input B is 0, again 0. If input A is 1, input B is 0, again 0, false. 0 means false, 1 means true. If the both input are true, then the output is true. Here it is written, AND gate outputs 1 true only when all its input are 1. Here you can see the fourth line, all inputs are 1, then the output is 1. Otherwise, it's 0. Then the second gate is OR gate. An OR gate output 1 if at least one of the input is 1. It performs the logical OR operation, representing a condition where only one or more input must be true for the output to be true. Here you can see if the input A is 0, input B is 0, then the output is 0. But if at least, here you can see an OR gate outputs 1 if at least one of the input is 1. Here you can see input A is 0, input B is 1, then the output is 1. Okay. So at least one input should be 1. Okay. 1 means true and 0 means false. Then the output will be true. So this is the OR gate. Now let's jump into the next gate, which is NOT gate. So a NOT gate, also called an inverter, has only one input and outputs the opposite value. If the input is 0, then the output is 1, and vice versa. Here you can see if the input is 0, then the output is 1. If input is 1, then output is 0. Because it has only one input, here written, has only one input and the output the opposite value. So this is the NOT gate. Next gate is NAND gate. So a NAND gate is the inverse of the AND gate. If the output is 0, only when all inputs are 1. For all other input combination, it outputs 1. NAND gates are universal, meaning they can be combined to form any other logic gates. Here you can see if input A is 0, input B is 0, then the output is 1, because it is the inverse of the AND gate. Okay, the both input are true, then the output will be false. Fifth gate is XOR gate. And XOR gate, exclusive OR gate, outputs 1 only when the inputs are different. It is commonly used in arithmetic and comparison operation. If both inputs are the same, the output is 0. Here you can see if the both input are same, then the output will be 0. Here both inputs are same, 1 1, then the output 0. If both inputs are different, then the output will be 1, which is true. So these basic gates can be interconnected in countless combinations to create more complex combination circuits for performing arithmetic operations, decision making, and data processing in computers and digital devices. So now let's move forward and see mathematical operations in combinational circuits. So combinational circuits can be used to perform arithmetic operations such as addition, subtractions, multiplications, and division. So a common example is the adder circuit, which is perform additional on binary numbers. So half adder is there. So the half adder is the simplest combination circuit for adding two single bit binary number. It consists of an XOR gate to add the two bits and AND gate to generate the carry bit. Then there is another adder is known as full adder. So the full adder is an extension of the half adder. It adds two single bit binary numbers and a carry bit from the previous operations. It uses XOR gates for the sum and AND or OR gates to handle the carry bit. So by combining these basic circuits, we can create more advanced circuits such as multiplexers, encoders, decoders, and the ALUs, arithmetic logical units, all fundamental in digital systems. So after understanding the combinational circuits, let's jump into the sequential circuits. So what are the sequential circuits? Sequential circuits are the circuits whose output depends not only on the current input values but also on the history of the inputs. So this means that sequential circuits have memory elements that allow them to store information about previous input. So these circuits can remember their previous states and use this information to influence future output. So the most fundamental type of memory element in sequential circuits is called flip-flop, which can be stored a single bit of data. Sequential circuits are used for tasks such as counting, data storage, and state machines, which are the critical in processors, memory devices, and other digital systems. So what are the flip-flops and the registers? A flip-flop is a digital device, meaning it has two stable states. It can store a bit of information, either 0 or 1. So the state of the flip-flop is controlled by clock pulses, which allow it to change its state at specific times. So flip-flops are used to build more complex memory elements like registers, which can also store multiple bits of data. So there are different types of flip-flops, like SR flip-flop. The SR is set reset. Flip flop has two input. One is set and another is reset. And D flip flop. The D means data flip flop. Captures the value of input on the rising edge of the clock signal. The input data is transferred to the output when the clock pulse is received. Then comes JK flip flop. The JK flip flop is a more versatile flip flop that can toggle its state, set or reset depending on its inputs. Then comes T flip flop. The toggle flip-flop changes its state on every clock pulses, making it ideal for creating counters. So these flip-flops form the basic memory units in sequential circuits, and multiple flip-flops can be combined to create registers and memory blocks. Now let's understand what is clocking. So in the digital circuits, clocking is the process which all operations in a chip are synchronized. A clock is a periodic signal that provides timing for all the operations inside the circuit. Without a clock, it would be difficult to coordinate the operations of the millions or billions of components on a chip. The clock signals in a square wave alternating between a high 1 and the low 0 state at a regular frequency. So the frequency of the clock signal determines the speed at which operations within the chip occur, and I repeat, and it is measured in hertz. For example, 1 gigahertz clock signal oscillates 1 billion times per second. So what are the clocking in sequential circuits? So in sequential circuits, the clock signal is used to control the state changes of memory elements, such as flip-flops. So the flip-flop only change the state on the rising or falling edge of the clock signal, which allow them to store information at a specific time. So the clock also synchronizes the operations other components in the system. For example, in a processor, the clock coordinates the fetching of instructions, the executions of arithmetic operations, and the storage of results. The speed of the clock determines how fast the processor can execute instructions. And modern processor can operate at clock speeds of several gigahertz, meaning they can perform billions of operations per second. What is clock domains? In clock systems, different parts of a chip may operate at different clock speeds. They are referred to as the clock domains, and managing the synchronization between them is a key challenge in chip design. Special techniques like clock domain crossing and synchronizations are used to ensure that the data is transferred reliably between different clock domains. So, in conclusion of this module, we explored the essential concepts of building circuits, focusing on combinational circuits, sequential circuits, and clocking. So, combinational circuits made from the basic logic gates are used for mathematical operations and decision-making tasks, while sequential circuits include memory elements like flip-flop that allow circuits to store and use past data that synchronize all operations within a chip, ensuring that the processor occur in a coordinated and timely manner. So these concepts form the foundations for designing digital systems, from simple circuits to complex microprocessors, and they are crucial for anyone interested in understanding how modern electronics work. As we continue to design faster, more efficient systems, the ability to build and understand these fundamental circuits will remain essentials in VLSI design. So in the next module, we will learn about VLSI designs and the Verilog part. So in the field of VLSI, very large scale integration design, engineers face the challenge of creating highly complex, efficient and reliable integrated circuits (ICs). So the development of these ICs require both precise design methodologies and tools that allow for accurate descriptions, simulations and verification. So this module will explore three key concepts or aspects of VLSI design. The first one is describing chips and the Verilog part, testing designs virtually simulations part, and quick prototyping with FPGAs. So each of these topics is integral of the process of developing, testing, and finalizing the VLSI design. So let's start with the what is Verilog. So Verilog is a hardware descriptions language (HDL) used to model and describe the behavior and structure of electronic system. It is one of the most widely used language for describing digital circuits and systems at different levels of abstraction, including the gate level, data flow level, and the behavioral level. So with Verilog, designers can write code that specifies the operation of a digital system, such as microprocessors, memory, or any other VLSI component. So Verilog allows designers to describe the functionality and timing behavior of digital circuits, enabling them to model how circuits will behave over the time and under different conditions. So this is very crucial in the VLSI design process as it allows engineers to conceptualize and validate complex design before actual hardware implementation. Now let's jump into the levels of abstractions in Verilog. So there are the different levels. So the first one is the behavioral level. So in this level, Verilog code is written to describe the functionality of the circuit without worrying about its detailed structure or the specific component used. So the designer specifies what the circuit should do, how it should do. For example, a designer might write code to describe how a circuit adds two numbers together without specifying the gates or register used. Fine. The second level is data flow level. At this level, the designer specifies the flow of data through the circuit, typically using continuous assignment and operation. So the focus here is still on the data movement and repeat and the logic of the circuit, but it begins to introduce some structure details such as the use of specific logic gates and or another gate. Third one is structural level. So this level involves the most detailed descriptions of the circuit, specifying exactly how different components are connected. This level of abstraction uses modules that represent actual hardware elements such as gates, flip-flops, and other fundamental components and show how these components are integrated. Then comes the gate level, the last level. So gate level description focuses on the actual gates used in the circuits and how inputs and outputs are connected. Verilog can be used to define a circuit entirely in terms of logic gates, creating an accurate low-level representation of the design. So after understanding the levels in the Verilog, let's understand what is simulations in VLSI design. So simulation is the process of testing digital design virtually using specialized software tools before implementing it in a hardware. Simulation allows designers to verify the correctness of their designs, check for the potential issues like timing, violations, and ensure the system behaves expected. Since VLSI design can be highly complex and contain millions of transistors, it is not practical to test them physically at every stage of the design process. Instead, simulations allow engineers to simulate the behavior of their design in a controlled virtual environment. So now let's understand now types of simulation in VLSI. So the first one is functional simulation. Functional simulation is a type of simulation checks where the design functions correctly. That is, whether the logic described in the Verilog code produces the expected result. Functional simulation does not take into account timing issues. It simply verifies the logic of the design. It is typically the first step in the simulation process as it helps catch basic errors in the design before the complex timing issues are considered. The second one is timing simulation. Timing simulations takes into the account delays associated with the circuit, such as propagation delays and setup hold time valuations. So this type of simulation is crucial in ensuring that the designs will work correctly at the speed the designer expects. Timing simulations are particularly important for the high-speed circuits like processors, where even small things errors can cause the design to fail. The third point is gate level simulation. So gate level simulations simulates the design at the lower level, typically using a netlist of logic gates. This type of simulation is used after a design has been synthesized, and it is helpful in verifying that the gate level implementation works as needed. The last type is post-synthesis simulation. After the design has been synthesized into a netlist, post-synthesis simulation is used to verify that the synthesized design matches the original specification and meets timing constraint. So this stage is critical in ensuring that the final design will be manufacturable. So now let's see some simulation tools. So there are several industry standard tools available for simulation in VLSI design. So here are the few. The first one is Model Sim, Advanced Simulation and Debugging. So Model Sim is one of the most widely used simulation tools for VLSI design. It supports both functional and timing simulation and can handle large designs. Model Sim is often used in combination with other tools like Cadence or Synopsys. Then the second is Vivado. Vivado is an integrated development environment IDE from Xilinx used for designing and testing FPGA-based systems. It includes simulation tools for both Verilog and VHDL designs and can be used to simulate both logic and timing. The third is Cadence. Cadence is another powerful simulation tool that supports both Verilog and VHDL. It is used very large scale design and can simulate everything from basic functional verification to complex system level validation. Now you will be wondering, what is the importance of simulation? So simulation is a critical step in VLSI design because it allows engineers to catch errors in early stage in the design process, reducing the risk of costly mistakes during fabrication. So virtual testing ensures that the design works as intended and meets the required specification before it is physically manufactured. Fine. So now after understanding the simulation part, so now let's understand what are FPGAs and how FPGAs are used in VLSI prototyping. So FPGAs are widely used for quick prototyping in VLSI design because they allow designers to implement and test their design before committing to the expensive and time-consuming process of manufacturing an ASIC, application-specific integrated circuit. With an FPGA, a designer can implement the Verilog descriptions of a chip and test it in hardware, allowing for early detections of issues that may not have been apparent in simulation. So what are the advantages of FPGAs for prototyping? First one is flexibility. FPGAs allow designers to make changes to the design even after implementation, providing great flexibility during the prototyping phase. The second one is rapid development. Unlike ASICs, which require weeks or months to fabricate, FPGAs can be programmed and reprogrammed quickly, making them ideal for fast iteration and testing. The third one is cost effective. FPGAs are much cheaper than fabricating a customer ASIC specifically for low volume production. This makes them an attractive option for prototyping new design. The fourth point is real world testing. Prototyping with an FPGA enables designers to test their design in real world conditions, which is often more informative than simulation alone. This allows for the detection of timing issues, more consumption problems, and other real world challenges. So there are FPGA tools and development environment. So designing for FPGA requires specialized software tools that allow engineers to write code, synthesize the design, and configure the FPGA. So some popular FPGA development tools include the Vivado, a powerful development suite for Xilinx FPGAs offering tools for simulation, synthesis, and programming. Then there is one Intel Quartus, a development tool for Intel FPGA, formerly Ultra, providing similar functionality for simulation and programming. So in conclusion of this module, we have explored three important aspects of describing and testing VLSI design: describing chip with Verilog, testing design with simulation, and quick prototyping with FPGAs. So Verilog is a powerful language for describing digital circuits, allowing engineers to model design at various levels of abstraction. Simulation enables engineers to test their design virtually, ensuring they work as expected before fabrication. FPGA provides flexible and cost-effective way to prototype VLSI design and test them in real-world scenarios. Together, these tools and techniques form a crucial part of the VLSI design process, allowing engineers to efficiently design, test, and prototype complex digital systems. Whether you are describing a simple logic gate or a full-scale processor, mastering these methods is essential for success in VLSI design. So in the next module, we will learn about the chips. So in the world of VLSI design, once the digital logic of the chip is defined and the high level design is completed, the next step is to bring the design to life physically. So the phase involves physical design, chip testing, and the software tools are used to facilitate this complex process. So in this module, we will cover these three key aspects. Okay, the physical design, the chip design or chip testing, and the software tools used for the trade. So what is physical design? Physical design is the process of converting a logical representation of a circuit, usually created using hardware descriptions languages like Verilog, into a physical layout that can be fabricated on a silicon wafer. So it involves creating the actual arrangement of the components such as transistors, gates, wires, and other circuit elements. So this process ensures that the physical placement of the components on the chip adheres to design rules while meeting performance goals such as speed, power consumption, and area efficiency. So physical design is a critical phase in the VLSI design flow as it directly impacts the chip's functionality and manufacturability. So what are the steps in physical design? The first is floor planning. So the floor planning is the first step in physical design where the designer decides the general layout of the chip, such as where different functional blocks will be placed. The floor plan defines the chip's overall size and organize the major components to minimize the distance between related components, reducing power consumption and improving performance. The second is placement. After the floor plan is defined, the next step is placement. In placement, individual components like standard cells means transistors and the logic gates are placed within the defined floor plan. So the goal is to minimize wire length while avoiding overlaps and ensuring there is enough space for routing. So the placement process affects not only the speed and the power of this circuit, but also the manufacturability of the chip. Third is routing. Once the components are placed, the next step is routing. Routing is the process of connecting the components with wires, creating the interconnections that allow signals to flow between the components. So the routing process must account for factors like signals integrity, crosstalk, and delays. The fourth one is clock tree synthesis. In complex design, clock signals are used to synchronize operations across the chip. So clock tree synthesis (CTS) is the process of designing and distributing the clock signals to all parts of the chip in such a way that it reaches each component at the correct time. Proper CTS ensures that the chip operates at the desired clock speed while minimizing clock skew, which can lead to timing errors. Then comes the design rule checking. So design rule checking is a process of verifying that the physical layout complies with the manufacturing rules of the foundry that will produce the chip. These rules ensures that the layout is manufacturable and that there are no issues that could cause defects during fabrication such as improperly spaced layers or wires. Then comes layout versus schematic. So after completing the placement and routing steps, the final physical layout must be checked against the original semantic check to ensure that the design is correct and consistent. This process, known as LVS, compares the logical representation of the design with the physical layout to ensure that no mistakes were made during the physical design phase. Then comes power and timing analysis. So the power and timing analysis checks ensures that the chip meets performance goals like timing closure, power consumption, like these. So the designer uses static timing analysis (STA) tools to check for timing violations and optimize the design. So after understanding the steps in physical design, So there are some key challenges in physical design as well. The first one is timing closure. Achieving timing closures means ensuring that every data path in the circuit meets setup and hold time requirements. So data arrives reliably within each clock cycle. This requires adjusting cell sizes, placements, and routing, and often involves iterative optimization using static timing analysis tools to eliminate timing violations without degrading other design metrics. Then comes the clock distribution. A critical challenge in synchronized design is the clock distribution, which involves building a well-balanced and low-skew clock tree that delivers the clock signals to all sequential elements, like flip-flops, simultaneously. Skew or delay mismatches can cause incorrect data capture, so techniques like H-tree structure, clock gating, and buffer insertion are used to optimize timing and the power. Then comes signal integrity. Maintaining signal integrity means preventing unwanted disturbance like crosstalks, reflection, or glitches that can corrupt data. So this requires careful routing, shielding critical nets, spacing signal lines properly, and managing load, capacitance, and drive strength to preserve signal quality. Then comes power consumption. Power efficiently is crucial. So especially in battery powered or heat sensitive devices, dynamic power and static power must be minimized through smart cell placement, use of low power batteries or libraries, power gating multi-voltage domains, and the clock gating strategies during the design. Then comes thermal management. As power density increases, heat concentration can cause thermal hotspots that affect performance and long-term reliability. So I repeat, so designer must plan for effective thermal distribution through floor planning, heat-aware placement, and spreading high-power components apart. Then comes area optimization. With the demand for more functionality, smaller form factors, physical designers must minimize chip area without violating design rules. So now let's move forward and see what is chip testing. So chip testing is the process of verifying that the fabricated chip works as expected and meets all the specified requirements. After the chip has been physically manufactured, it undergoes extensive testing to detect any defects, manufacturing errors, or performance issues. So testing ensures that the chip performs reliably under real-world conditions. So testing is essential to guarantee that the chip will function as intended in various electronic systems. It helps identifying issues like timing errors, electrical failures, and logical problems that could affect the chip's functionality. So what are the types of chips testing? The first one is functional testing. It checks if the chip gives correct output for given input or not. Then comes the parametric testing. It measures electronic or electrical parameters to meet design specifications. Then comes boundary scan testing. It tests pin level connections using scan chains. Then comes built-in self-test. Enables the chip to test itself internally. Then comes delay and timing testing. Verifies signal timing meets speed requirements. Then comes stress testing. It tests chip reliability under the extreme conditions. Then comes the regression testing, which ensures updates and allow you to don't break existing functions. So after understanding types of chip testing, now let's see some challenges in chip testing. The first one is high testing cost. So chips testing is a resource intensive process that requires specialized equipment, skilled engineers, and significant computational resources. As chip complexity increases with the billions of transistors and the multiple cores, the cost of development and running thorough test cases grow substantially. Then comes limited test coverage. Ensuring full test coverage, meaning every possible fault or failure is tested, is extremely difficult in modern VLSI design. Complex logic, multiple function modes, and deep signal path make it challenging to simulate and test all corner cases. Then comes speed and efficiency. In high volume chip production, testing must be both fast and efficient to keep up with demand. So long or overly detailed tests can slow down manufacturing lines. Then comes fault detection difficulty. Some faults are intermittent, rare, or only appear under specific conditions, making them difficult to detect. Then comes power and thermal issues. Certain test scenarios, especially those that exercise many transistors simultaneously, can cause abnormal spikes in power consumption and heat generation. Then come post-silicon debugging. After the chip is fabricated, debugging any functional or performance issues becomes significantly more difficult due to limited observability and controllability of internal nodes. So now let's see some software tools used in VLSI design. So in VLSI design, software tools may play a pivotal role in automating the design, testing, and the verification process. So these tools help streamline the complex tasks involved in designing chips, checking for design errors, and ensuring that the physical layout can be fabricated successfully. So there are some most commonly used software tools in VLSI design and categorized into some following types, like the CAD tools. CAD tools are used for designing and laying out integrated circuits. They allow designers to create semantics, perform simulation, and create physical layouts for the chip. So examples are Cadence, Synopsys, and Mentor Graphics. Then comes the simulation tools. Simulation tools allow designers to test and verify their designs before fabrication. These tools provide virtual environments in which designers can test functionality and performance of their circuits, detect errors, and optimize design. Examples are ModelSim, Vivado, Cadence. Then comes synthesis tools. Synthesis tools convert high-level design descriptions into gate-level representation. So this is a critical step before physical design can begin, as it prepares the design for implementation in hardware. Examples are Synopsys Design Compiler and the Cadence Genus. Then comes place and route tools. These tools help automate the placement and routing of components in the physical design phase. They ensure that components are optimally placed on the chip and that all connections are properly routed to minimize delays and power consumption. Examples are Cadence Invoce and Synopsys IC Compiler. Then comes timing analysis tool. Timing analysis tools are used to verify that the chip meets the required timing constant. They analyze the signal delays and ensure that the chip operates at the desired clock frequency without the errors. Examples are Prime Time by Synopsys, Tempus by Cadence. So in conclusion, in this module, we have explored the essential aspect of chip design, including physical design and the chip testing and the tools of the trade used in the VLSI design process. So physical design involves arranging components, placing them, and routing them to create a functionally chip layout. So congratulations on completing the VLSI design course. You have taken a big step in leveraging design to enhance your chip making process. So now it's time to put your learning into action. Try integrating these VLSI design concept into your workflows and experiment with design to optimize your project efficiency. Thank you, and keep learning by Simplilearn.
Staying ahead in your career requires continuous learning and upskilling. Whether you're a student aiming to learn today's top skills or a working professional looking to advance your career, we've got you covered. Explore our impressive catalog of certification programs in cutting-edge domains, including data science, cloud computing, cybersecurity, AI, machine learning, or digital marketing. Designed in collaboration with leading universities and top corporations, and delivered by industry experts, choose any of our programs and set yourself on the path to career success. Click the link in the description to know more.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.